vibration class. So today we'll be looking at vibrations or sound waves produced in pipes. Now for pipes, we have two types. It's either it is an open pipe or a closed pipe. Alright? So we have open and closed. Now for an open pipe, the two sides, if it is a pipe or a tube, the two sides, the two ends are open. So we'll call this one open, an open pipe. But if one of the side of this tube or this pipe is closed, it's called a closed pipe. So it means something like this. We have one, then this side of it is closed. So if this is the scenario, we'll take them one after the other. So for the first one, let's talk about the closed pipe, the frequency produced in a closed pipe. So for a closed pipe, when air is blown from the open end into a closed pipe, the air molecules in the pipe begins to hit the surface or the body of this pipe, thereby producing sound. So the waveform for the first notes or the lowest possible frequency that will produce the sound, the waveform is going to look like this. Immediately the air molecules is produced or is blown into this pipe, you find out that there is going to be sound wave, and the sound wave, the loop of the sound wave will look like this. So what actually happens is this: immediately you blow air into this pipe, the air molecules, as they are going into the pipe, hitting the surface, when they get to this bottom, since there is no opening, they reverse back and follow this path. So at the end of the day, we are still going to have a stationary wave or standing wave. So again, points where there is no vibration is called the node. So we have a node here, while here, the open end where it's moving, we have what? Antinodes. So from here to here is a waveform is produced. So we remember what we said, that this is the length of the hair column. Now in terms of the wavelengths, how many wavelengths is here? If you observe closely, from this antinode to this node is 1/4 of a cycle. All right, let's draw it out. We have a loop like this. Okay, let's draw it well. So if the pipe is lying down, let's say it's lying down horizontally like this, we have this like this, we have this. So you now have your node here, then our antinode here. So from here to here is have 1/4 of a quadrant, because the full quadrant will be something like this. So just here to here, we cut into 4. So here to here is 1/4 of a quadrant. So which means our wavelength, the wavelength produced, just this part, is going to be 1/4 lambda. So that's why we can now say that the length of the hair column is same thing as 1/4 lambda. 1/4 lambda. So if we are going to get the frequency again like we did before, recall that the velocity is given by F ladder for wave, equation of wave velocity. So if our frequency is going to be V over lambda. Now for this case, for an open pipe, the frequency will now be F equals to V over, what is the wavelength now? The wavelength, okay, let's come back here and get the formula for wavelength. So we said that length is 1/4 lambda. So if you make the wavelength instead of the formula, that will be 4L. So which means for this case, this wavelength now will be 4L. So this is now 4L. Recall, this is the first sound. The first sound, so which goes with the first frequency. And the first frequency is called the fundamental frequency. So for the first case, we now have our F naught. The first possible frequency that will produce the first notes is called the fundamental frequency, is the lowest. So that is what we have. Now if we are going to get the next frequency, it means we have two notes. So let's get the case for this. Let's draw the second case. So if this is a pipe, this is the closed end. This is the closed end. This is the open end. Now for the next vibration or sound wave that we produced, after the first one has been produced, we'll be having something like this. So this is the first, which we've already drawn before. Now the second we now have to go like this. So now something like this. So this is for the second vibration that we produced. So again, from this end to this end is called the length L. So let's now still look for the wavelength. The wavelength that will be equivalent to this length. So if we say this point, there's no vibration. So this is node. This is an antinode. This is node. This is an antinode. In fact, it's worth noting here that for the sound wave produced in the pipe, for this case a closed pipe, it always ends with a node. So it always ends with an antinode, because this end there's nowhere for the sound to pass out, so there's no vibration here. So it always ends out with an antinode, just like this first case. So now let's measure the wavelength for this from here to here. The wavelength will now be this node to this node, because the distance between two consecutive nodes is half wavelength. So from here to here is 1/4. So which means we are having 1/2 lambda in this case, then 1/4 lambda in this case. So two of them together will give us what? Will give us 3/4. That will be 3/4. What I'm saying is 1/2 plus 1/4. That should be, okay, when you raise this up, this will be 2/4 plus 1/4. Just multiply this stuff by 2, multiply the denominator by 2. So now I have 3/4 lambda. So for the second waveform in a closed pipe, this is what we are having. It always ends with an antinode, since this other end is open. So the wavelength will be 3/4. So that is to say, we can now say that the length of this string, the length of the head column in this pipe, is equivalent to 3/4 of the wavelength. So if that is the case, we can also get the velocity for the second. We can also get the frequency for this waveform for closed pipe. So the frequency, as already said before, is V/lambda. The lambda here, okay, this is lambda. The lambda here will be we'll cross multiply now, so that will be 4L/3. That will be our lambda. Let's clean all this. So which means if we are getting this will now be V/4L/3. That is, we've substituted for lambda. Substituted for lambda, which is 4L/3. So when you rearrange, your frequency will now be 3V/4L. So let's put that one again out. Let's put it out. So the first case, if you recall, was V/4L. That is the first frequency, fundamental frequency. The second frequency now is now what? 3V/4L. So now 3V/4L. So if you want to do for the third, you can also do it. So let's see what we have. Now for the third, we now have something of this nature. Now let's put the pipe. Let it be lined horizontally. So the first frequency is something like this. The second one we just drew. So this was the first. The second ended here. So the third is now ending here. So we are now having node. It always ends with an antinode. So here is another antinode. So the length of the hair column in this pipe is from here to here, So this is the length. So for this case, what will now be the wavelength? We have to also measure. So like we said before, here to here is half wavelength. Here to here is another half wavelength, making a full wavelength. Then here to here is 1/4. So now I have one whole number 1/4 lambda. When you convert it to improper fraction, that will be 5/4 lambda. So it means now that this length, the length of the hair column, in terms of the wavelength, will be 5/4 lambda. So if you make your lambda straight up formula, lambda will be what? This will times this now. 4L/5. So for the third frequency, the value for the third frequency, going by our formula, will now be will now be okay. So let's pause it out here.